So let's sum up what we've learned about E and M so far. As it turns out, even though that sounds like a really scary proposition, I can do that by writing down just a few equations. The first one would be this. Move this paper over. E dot dA is equal to Q enclosed over epsilon naught, right? Gauss's law. I won't write that down, it's okay. Gauss's law. We've seen this, the closed integral of the electric flux. E dot dA is the electric flux. If it's the differential element of the electric flux, right? E dot A is the flux. But if I'm going to integrate that over some area, I form the differential dA. I integrate over the whole area, which is what this closed integral means. And that is then equal to Q enclosed over epsilon naught. This is Gauss's law. And like we said, it's not always useful, but it is always true. And it is, in principle at least, we can always find the electric field this way, although the integration might be difficult or even impossible at some points. But in essence, this sums up the relationship between an electric field and the charge or charges that produce it. Now, in this course, we didn't really look at this one. This is Gauss's law for magnetism. Notice I've got the magnetic flux here integrated over some closed area, just like I had the electric flux. We certainly talked about the magnetic flux. We didn't see this expression, though. This actually turns out to be identically zero. We did talk about some effects of this. For instance, we mentioned that magnetic fields formed closed loops, that is, they bite their own tails. That's actually a consequence of this, because if you have some sort of closed surface, if a magnetic field line goes into that surface, it has to go back out because they form loops. And so the total flux through the surface has to be zero, because if the loops don't go out, then they don't come back in. They can just stay inside the surface, or they can be completely outside the surface, or they can go in and then come out. Those are your only options. So this is Gauss's law for magnetism. This also has the ramification of no magnetic monopoles, right? The field lines bite their own tails because they come from dipoles. So that's Gauss's law for magnetism. We didn't look at this explicitly in this course, but it is a thing. We did, of course, look at this one. Now, if I just write normal integral E dot ds, that is the electric field integrated over some path, I get the electric potential of that field. I should say the electric potential giving rise to that field. If this is a closed integral, then I get Faraday's law, which is the EMF induced in a coil. Sorry, this should be a D here. Due to a changing magnetic flux. And of course, there might be an N here to tell you how many turns of wire you're going through. But in general, this is Faraday's law, the law of magnetic induction. And then there's one more that we've seen, which is this. The same idea of integrating a magnetic field over some closed path, right? Which is equal to mu naught I enclosed. So, just to sum up here, I should say these are together called Maxwell's equations, which you might go, well, hold up, this is Gauss's law, this is another Gauss's law, this is Faraday's law, this is Ampere's law. What did Maxwell have to do with this? Well, James Clerk Maxwell was a brilliant, phenomenal physicist who did a lot of work with these equations, did a lot of work with electricity and magnetism, but as it turns out, Maxwell did contribute something to this series of equations, which I need to amend in just a second. But these are the Maxwell equations, or at least they're close to the Maxwell equations. And then, along with the Coulomb force law, I get basically all of electricity and magnetism in a very succinct, very elegant set of equations. These are all in integral form. You can also find them in differential form, make that a vector. But this is Maxwell's equations. Now, what did Ampere add to it? What did Maxwell add to it? He had actually added something to Ampere's law. And to see why it's necessary, let's go back a few chapters to a capacitor, which we'll assume is charging. It doesn't have to be charging. It could be discharging if you want to. We're going to assume this capacitor is charging. Now, if it's charging, I've got a non-zero current on the left side of this plate. I've got a non-zero current on the right side of this plate. Remember where this current comes from. Some EMF is placing charges on this plate. The charges that get placed on this plate kick off charges from this plate and the current flows down the wire. But it's not true to say that there's actually a current, at least in this sense, flowing across the gap. It can't do that. If current flows across the gap, that's a catastrophic failure of the capacitor, right? But we do know that there's an electric field here. So, as shown in the green arrows. What I want to do is, with my poor artistic skills, I want to draw an Amperian loop there, surrounding that wire. Now, what I want to suggest is that if this is a closed loop, it bounds a surface. Which surface, though? I go, well, it bounds that circle that it is covering up, and you would be right. It does bound this circle, and that's how we've been using it. And clearly, if that's the surface I'm choosing, then Ampere's law works just fine. The current enclosed is 0. Let me write down Ampere's law so you see what I'm talking about. B dot ds, the integral, closed integral, B dot ds, is equal to mu naught I enclosed. Okay, so for this line, this ds that bounds this surface, I hope we can see that this integral is not 0, right? However, is that the only surface bounded by this line? No, it's not. In fact, there are an infinite amount of surfaces bounded by that line. Let me draw another one, if I can. So imagine that this surface is like the rim of a glass. And this is the surface bounded by this line. So this line, the first time I wrote down, I shaded it in blue and said the line is bounding the circle. But now let this line bound this curved surface like it's the rim of a glass. That's one surface. Now, how much current is passing through that surface? Well, none, right? This surface has an electric field passing through it, but because I'm going through the gap in the orange case for that surface, B dot ds, the same ds gives you exactly 0 because there is no I enclosed. I enclosed is 0. So how can this be? This shouldn't be that. It shouldn't matter which surface I integrate over, or not. I'm not even integrating over a surface. It shouldn't matter which surface is bounded by this line integral if this is really going to work. And so this is a big problem. What Ampere didn't recognize was that I can draw more than several surfaces. What Maxwell did realize is that there is something going on here that is like a current. That's about the best I can do with it for now. It's kind of strange to think about, but if there's something going on here, there's clearly going to be some sort of magnetic field contribution here. So how can we handle that? Well, let me go back to this sheet. What Ampere said, I keep saying that, what Maxwell said is that we need to amend this I enclosed and add in, so I got the wrong pen, add in plus this term I sub d, which we call the displacement current, where the displacement current I sub d is defined as epsilon naught times d phi e dt. The change in electric flux per unit time. Now, is there an electric flux through this orange surface? Yes. Is it changing in time? Well, if the current is changing in time, that means the charge on the capacitor is changing in time, which means the flux through that field is absolutely changing. Language is failing me. The flux through this surface is changing in time. And so, yes, there is a non-zero d phi dt. What Maxwell says is we can consider that to be this displacement current, and that handles this problem. Nice, I should say this problem, right? This problem where I get a zero from the integral if I look at this surface, and a non-zero integral if I look at this other surface. So in that case, no matter which surface I look at, as long as that particular line bounds that surface, I get that there's a magnetic field contribution. Notice if I'm looking at the blue surface, I enclosed contributes and I displacement does not. If I'm looking at the orange surface, I displacement contributes, I enclosed does not. So this is really interesting. What this means is that if I have a changing magnetic flux, if I have a changing electric flux, I get a magnetic field. Let me say that again. If I have a changing electric flux, I get a magnetic field right here. We've already seen with Faraday's law of induction that if I have a changing magnetic flux, I get an electric field, right? We looked at this in terms of getting an EMF, but EMFs and fields don't separate themselves. All fields are associated with a potential, and all potentials give rise to a field. So I can't just say that, well, this is an EMF, not an electric field. A changing magnetic flux gets me an electric field. A changing electric flux gets me a magnetic field. I don't get one without the other. That's really interesting. This is why we call electricity and magnetism electromagnetism, right? They are actually inseparable phenomena. It actually turns out they arise from the same thing, charge, right? Electric fields arise from charges. Magnetic fields arise from moving charges. So they are not separate like it seems like they're separate. If I'm holding a bar magnet in my hand, it's not obvious to me that that has any sort of electrical connection. But as it turns out, electricity and magnetism are two sides of the same coin. There is one other thing that Maxwell discovered, which is really interesting, which leads us right into what we're talking about in this chapter. We know that the speed of light is some constant c, usually written as 3 times 10 to the 8th meters per second, or 2.99 times 10 to the 8th meters per second. But it's some constant c, and that's measurable in the laboratory. Well, lo and behold, it's also calculable from this expression. One over root epsilon naught mu naught. Now this is our electrical constant. This is our vacuum permittivity. And this is our magnetic vacuum permeability. So I've got the constant associated with electric fields. I've got the constant associated with magnetic fields. Interestingly enough, take this product, invert the square root of it, and you get the speed of light, which we are now going to start calling the speed of an electromagnetic wave. As it turns out, visible light is just one example of the electromagnetic spectrum. There's no explanation for why both of these constants appear together, except for the fact that electricity and magnetism are inextricably connected.